This conference commemorates the life and achievements of Abdus Salam. It's therefore incumbent upon me to begin by drawing a picture of the man with a few private and perhaps more intimate reminiscences that may convey something about the greatness, genius, and humanity of the person. I know that some of you have worked with him in some capacity at some stage, but I doubt that very few of you will have had the privilege of interacting 17 years or more with him, as I have done. First as an undergraduate, then as a postgraduate, a postdoc, and eventually as an academic colleague and scientific collaborator. I'm going to cover the period 1959 to 1976, when I left for Tasmania. And I was closely involved with Salam during that period. I know there are a few others here present who can competently fill in the full portrait of Salam. If certain members of the audience have heard my little vignettes of him before, I do apologize in advance, but I hope these reminiscences you may at least share in reliving some of the fond memories of Salam. Salam was a man in a hurry. His reputation preceded him everywhere. As a lowly undergraduate student, I first came across him in 1959 when we had to choose our third-year specialty by making a selective tour of the various departments at Imperial College. At that time, Salam was housed actually in the maths section. This is in the Huxley building, before he moved to physics in 1960. And I can vividly remember his verve and vivacity as we entered his room, and he explained to us his latest pet project. That was the chiral symmetry and gamma-5 invariance for favoring massless left-handed neutrinos and leading to parity violation. Of course, that discourse at that stage, we were just raw undergraduates. It went right over our heads, but they inspired us, and they certainly coaxed me to turn to theoretical physics as my specialty in final year. I'm sure others have succumbed to Salam's persuasive abilities on whatever topic he expounded. Well, that very year he taught us advanced quantum mechanics a la Dirac, and Dirac he idolized. By the way, Dirac was not his PhD supervisor. It was Fred Hoyle who was his PhD supervisor. A lot of people don't know that. Well, that very year, he taught us, as a quantum mechanics, and his lectures seemed pretty good to me. So I decided, well, let's try a PhD in theoretical physics rather than optics, which I was originally interested in. During those years, Salam's areas of interest were on the vanishing of renormalization constants for composite systems. He was very interested in Lie groups at the time, and he was interested in the gauge technique. Now, he took a keen interest in my own research topic, and he would inquire every morning, how are you getting on? What have you done? God, you can imagine the amount of pressure that it put on me and also on all these other students. He was always bubbling with new ideas, and postgraduates found it very hard to survive the change of tack or emphasis as we proceeded. It was terrible, but it steeled us, I can tell you that. That period saw the development of the Eightfold Way. And I can very well remember Salam's heated arguments with Neyman that came from his office across the corridor. Salam, of course, lost out on the Eightfold Way because of his insistence on a fundamental Sakata triplet. So you can say that he tripped up on that. However, in hindsight, was he really that far out? Think quarks, and you'll agree that his intuition was amazing. Yes, he could make mistakes, and who doesn't? But on most things, his inspiration was spot on. When I sometimes asked him, where did he get his latest idea? He'd sit back in his chair and give a wicked smile and point upwards. He always moved on to something new when an old idea was played out and established. He was never one for potboilers, and he never suffered fools gladly, in public anyway. In private, he could be quite scathing with the work of some people, I can tell you. And he actually referred to them as sometimes as tom-tits. He would refer to them as broken reeds, and even worse, as youths. However, as I say, in public he was absolutely polite, and he always encouraged anyone who presented a new idea. He was really fantastic as far as that went. If there's one lesson that Salam has taught me, it's that one should not be ashamed to move on if a concept is not bearing fruit. And that may explain why there was always great anticipation whenever he delivered a lecture on some topic. The expectation of the audience was that he would spring something new on them, and he always did. Salam was a demon for hard work. For instance, around about 1967, he had an appendectomy. I visited him in hospital 2 days after his operation, and it wasn't long before he launched into discussing multi-quark states and their current algebras, despite his obvious physical discomfort. He was a well-traveled person, and especially during 1962 to 1965, when in the process of setting up ICTP with Budinich. Funding problems beset him for a good while. It would actually irritate him immensely. He would rile at the politicians who opposed his initiatives, including, by the way, the Australian representatives on UNESCO. Anyway, owing to his regrettable experiences in Pakistan after leaving Cambridge and his constant bemoaning of the decline of Islamic science, he felt a driving need to found such a center to assist the third world countries. He had a special affinity for isolated scientific personnel who, like himself at first, struggled to keep abreast of the latest developments. He believed that initially concentrating on theoretical studies would serve the purpose, as it would cost relatively little, but represented the forefront of physics. Later on, the center could be used as a launchpad for other branches of science, as indeed it has done. At Imperial College and later at Trieste, Salam became a major magnet for Pakistani students, as well as those from Africa and Latin America. And we also had a few Greeks, actually, too, if I remember correctly. The place was abuzz with them, and Salam took great pains to foster their work. His initiatives and his constant movement gave him very little time for relaxations. And I vividly remember several meetings that John Strathdy and I had with him in the Hotel Foyer at Trieste after his energy-sapping perambulations. He used to work on the plane as well. I think he was able to maintain his stamina because he was an early riser and he went to bed early too. My request that he'd not ring me before 7 a.m. unless there was an emergency must have tested his self-control. Always the perfect host, he warmly welcomed new visitors to Imperial College and ICTP by inviting them to dinner or wherever else. He was not in the least pretentious about the venue. I recall one occasion at IC when Bruno Zumino came to give us a lecture. Instead of taking him to the staff club for lunch, he opted for the college cafeteria so he could mingle with the plebs. This tells you something about it. He says he was a humble man. Yes, that proves it. And he actually enjoyed the canteen fare, which is surprising. But anyway, the thing that most impressed John and I about his eating habits, really did impress us, was when we were eating fish. Salam would crunch his way through the spine and the bones, leaving only the tail and the head. Couldn't believe it. If waiters were tardy with producing the bill, Salam would get up and leave the trattoria when his patients ran out, and you should have seen the sight of the cameriere running after him with Il Conto. It was pure comedy. At coffee, he would often ruminate about the heyday of Arabic science and how vital it was for the Middle Ages for passing the Greek legacy through Spain. Anyway, above all, Salam impressed upon us the importance of tackling challenging problems to prospect for new scientific fields and abandon raking over old coals if one wants to make one's mark. He lived up to that precept throughout his life, in spite of accusations that he had a scattergun approach to physics, you know, how many balls he could juggle. It's a lesson that some young scientists today should heed. In his last years, despite his grave illness, he addressed the puzzle as to why certain life forms have particular handedness. Now, really, what could be more fundamental and significant than that? I know that I miss his wise words, his friendship, his guidance, his generosity, and his humanity. This conference is therefore a personal acknowledgement of how much he helped to shape my own career. More widely, it's a timely reminder of how much the scientific landscape and international developments owe to him. And the ICTP is a permanent testament to that. So that brings me then to the scientific part of my talk. The material which I'm going to present is sufficiently different from other attempts at unification of forces that I rather fancy Salam might have given them a nod of approval. I don't know. Anyway, when you're at the end of the world like I am, and how about you can do weird things, all right? 2 years ago at the Dyson 90th anniversary conference, I outlined how it's possible to unify gravity with the simplest of all forces, electromagnetism. Now you all say, oh, Klein and Kaluza did that. Of course they did. But there's a difference here. The way I'm going to do it is to introduce a single complex anti-commuting Lorentz scalar variable. If he had only done that, he'd have got his unification. It's as simple as that. You'd never get in any infinite KK modes. That's gone. Well, my partner in crime, Paul Stack, and I have made considerable progress since then. And I'm not going to try to summarize how to unify gravity with the other forces of nature through a really quite simple, almost simple-minded supermetric. Our attempts in this direction have been motivated by the parlous state of particle physics. Some of you are not going to like what I'm going to say now. I'm expecting some catcalls. I would claim, I'm an old fossil now, that the snail pace of progress in this area over the last 30 years has been not very great. Apart from the timely discovery of the Higgs boson and the huge amount of effort that's gone into producing that, and apart also from the emergence of these tetraquark and pentaquark states which have come up, and of course there have been significant astrophysical advances, there's actually very little to celebrate in our attempts to unravel nature at the basic level. This is in spite of determined, quasi-Herculean efforts of theorists who have persistently espoused and promoted some really very clever ideas. But I'm afraid so far nature has stubbornly refused to cooperate by providing us with unequivocal experimental signs of supersymmetry, of strings, of brains, and other very ingenious proposals. I'm not belittling the work of these people. It's fantastic, but nature won't cooperate. It seems that the simple standard model of particles and cosmology reigns supreme. Nonetheless, lots of parameters, and they've spurred theorists to try to reduce the number of arbitrary constants, okay? Well, many schemes have been put forward. They introduce scalar fields, the higher groups, sterile particles, and so on and so forth. It seems to me that these ideas actually are very much hit or miss, and they do seem to lack a fundamental basis. I think Salam might have looked askance at them. Anyway, here we go. I'm going to give you my own version of this. It's probably wrong anyway, but let's have a go. Unless you try, you never know. Now, for many years, could you come down, please? For many years, we've become accustomed to the notion of space-time events with local fields belonging to some representation of some group interacting at a particular site and time. So let's, yeah, okay. Okay. The space-time, no, it's fine. The space-time continuum serves as a backdrop for the when and the where of an event. Of course, we all know that. But until you specify the fields involved in the interaction, you always leave the what of the action open. It's got to be determined by experiment, of course. Now, you've got to realize that any event necessarily consists of some kind of change. Otherwise, it's not an event. It consists of a transaction or a change of property at a location. And it's usually communicated by a gauge field anyway. So it occurred to me that it might be possible to provide a mathematical backdrop for the what of an event, for the properties of, or attributes of the participating fields, by invoking a new kind of space, a property space, with its own set of coordinates. As far as we can tell, they're only finite. Now, oh, have I gone far? It's moved on. Let's go back. So the question is how to incorporate property mathematically. And the idea is just try using anti-commuting complex numbers, of which there are only a finite number. That's all you need. Let's have a go at that. It might prove wrong, but I'll talk about that later. It's certainly a weird idea. So how, you might wonder, why did you choose them anti-commuting? Well, if somebody is rich, they can't be doubly rich. Now, of course, it can be doubly rich, but I mean, if you're rich, you're either rich or you're poor, all right? Or you're either pessimistic or you're optimistic. You can't be double that. If you're red, you're red. If you're green, you're green. If you're anti-green, so on and so forth. So when you have a complex quantity like zeta, it can't doubly have it. That's one of the reasons why I've chosen that. Of course, an entity could be several things. You can be rich and you can be pessimistic, you see, and that kind of thing. So it's a melange of properties, and it's a finite one. And you must allow for the opposite attributes, so you have to allow for complex conjugates. That's why it's complex. And the interesting thing is that with this kind of idea, you can get generations automatically. The point is there are finite numbers of these zeta bar zeta scalars, and well, you can't have any of these. You can't have any number of these. And you might be able to see what generations turn up. So it's quite similar, actually, to an extended supersymmetry, except there's nothing to do with spin. It's properties we're talking about. So the question is, how many do you choose? Well, I've taken my inspiration from people who have done grand unified theories, and it seems in this kind of description that I need at least 5, otherwise I cannot accommodate the known generations of leptons and quarks. And in addition to finding these leptons and quarks, you find that you get more states than just that, but a finite number of them. That's the important thing, including ones which are neutral and therefore sterile, which may or may not have something to do with dark matter. That's a possibility. So what framework do I use? I have a framework of where, when, and what. And the super-Bose, think of them as a checkerboard, and the super-Bose fields are going to be even functions of the powers of zeta, and the super-Fermi fields are going to be odd functions of the thing. And what you have to do is, to get the whole of the action, you have to integrate not just over space-time, but you have to integrate over property as well. That's the idea. So I'm going to now, this is the notation I'm going to use. I'm going to use Latin letters for space-time, the usual 1, 2, 3. I'm going to use 1, 2, 3 for Greek letters for chronicity or color. And I'm going to reserve 0 and 4 for being neutrino-like and electrical. Those are the 5 properties I need. With those, I find I can do everything. There are certain quantum numbers associated with these. I'm going to come back to that when I talk about the gauge fields. Just bear this in mind. Okay, so where then do the leptons and quarks reside if you're going to do such a thing? Well, it's quite easy to see where the leptons go. You have a neutrino-like object, the zeta 0, and then you have a charged lepton-like object, the zeta 4, and you're allowed to have powers of these invariants, z, which I call zeta bar zeta. Now, when you do this sort of thing, you find various numbers of 5s and 10s and so on. And it turns out that the quark generations actually come quite subtly. They come in these melanges. First one on the left, the second one on the right, and the interesting one is the third one. The third one, it turns out, it's not quite, it could be, it's either two doublets, it depends on the assignments here. But the point is there has to be another quark which has the property of zeta colored, bar this, and for this. So that kind of object. I'm predicting this scheme is not the same as the standard model. There has to be another quark of charge minus 4/3 in the third generation. It has to be that. And the question is, where does it lie? Well, who knows? I originally suggested lepton, anti-lepton collisions for producing this. And maybe in this 750 GeV stuff that suddenly appeared at CERN might be a bound state of XX bar. Who knows? I mean, actually, that would be, I just don't know, obviously. You get a few more D-type quarks and a couple more leptons. This is what happens. So you can accommodate the known particles this way. The more interesting thing is, where the hell do the force fields arise? This is really very interesting. So what I've gone is, I go to an extended metric and separation in location and in type. So you have here a separation of an event where the metric is given by the product of two frame vectors, essentially. And there are all these stupid factors, these minus 1 factors to various powers, and you've got to get that right, and it took us 6 months to get all these factors right. It's actually quite painful. You've got to make sure the order's right and the factors are right and so on. And it turns out that if you're dealing with flat space, of course, you've got Gaussian and flat property separation. Notice, incidentally, that in order to make the separation have the dimensions of length squared, you've got to introduce a fundamental length L. This is pretty interesting too. Well, once you've set it up, then the metric tensor has to transform in a certain way. Obviously, it has to. And it turns out that if you want to make a local transformation like this, where the property is being rotated, which depends on x, then you have to introduce a frame vector in the property space-time sector, which has the following form, this one here. Otherwise, you can't do it. And if you do that, then simply the transformation rules for the metric are nothing but gauge transformations. You're not surprised, really, by that. It turns out it drops out perfectly. Now, the transformation rules of the metric are just the gauge transformations. So you might say this is all arbitrary and so on. Actually, there's very, very little room for maneuver where you put the gauge field. It's got to be in the space-time property element. It's got to be overall fermionic. It has to involve the product of the gauge field and the coordinate. And its placement in this makes absolute sense, because gauge fields obviously communicate property from one location to another location. It's got to be there. And if you look at ordinary Planck-Kaluza, it's the diagonal element, which is very similar, isn't it? And the only freedom that I have left, without destroying the gauge symmetry of the group, is to include these kind of invariants, the sort of the nothings, basically, and the powers of these things. So the extended metric, it's a very simple metric, actually. It contains an element in the properties, in the space-time sector, and then there is the property space-time. You can put the polynomials of these z's, as I've called them, these sterile things, in them. They're like the mass thing, the mass term in the Schwarzschild solution. It's quite similar to that. The coefficients, the little CNs, are kind of property curvature coefficients. Well, then the rest of the stuff is actually just turning the handle. That's all you have to do. So what you have to do now is to work out the super Ricci scalar, which is the contraction of the Ricci scalar. All these wretched, I'd written it in Palatini form, which you'll probably be familiar with various factors, which took us ages to get right, but anyway, we've done it all now. And the Christoffel symbol is another mess with factors of -1s and +1s. And when you've done everything, you have, of course, to integrate over space-time, and you have to integrate over property. Well, when you integrate over property, you always get the following combination. You get a term which is the curvature of the gravitational field. Everybody's happy with that, this kind of Newtonian bit. So the standard gravitational bit. And then you're followed by the next term, which is the gauge field term. And just drops out like a charm. It just drops out. It has to be there. It has to be gauge invariant. It can only be this. And it does fall out perfectly. And in addition, you have a coefficient with a kind of cosmological term in it. Of course, as I said, the gauge field is just the standard Yang-Millsian thing. Now, at first, we had to do this using algebraic computer programs because there are all these pluses and minuses, and it just drove it. It's hell doing it by hand, I can assure you. And you make mistakes so easily. But anyway, finally, Paul Stack was very good, my collaborator. He found a way of implementing all this on Mathematica. Just actually had to redefine all the functions and everything, but he's done it. And anyway, finally, we have found a way of working out these coefficients of the gravitational part and the gauge part and the cosmological term without using without using Mathematica. And thank goodness, this is a relief to me because it means I can get on and do it myself. The coefficients for these various terms can be found in the conference proceeding. I'll tell you later on. I'll give you a reference and you can find all these things. The bonus of this way of doing things is that the Ricci tensor, the stress tensor of the gauge field actually comes just in the right place, and it's a part of the Riemann, of the super Riemann-Ricci tensor. That's all it is. And it comes with the right sign in the right place, and you don't have to do anything. It just drops out with the correct sign and everything. So what about the matter fields? Well, in the matter, when you include matter fields, you've got to do something similar. You have to integrate over property of the usual, this is a very standard Lagrange, where you have the super Bose field and the super Fermi fields. Incidentally, I hate the term super, but I'm stuck with it. Everybody uses super when they've got something extra. Now, in order to get an answer for this, you've got to make sure, this is a subtle point, you've got to make sure that these fields are self-dual. What I mean by that is, when you write down the fields as power series expansions in the property coordinates, you know that if you change zeta to zeta bar, which means reflecting about the diagonal, you're going to get the complex conjugate. This is kind of obvious. But what is not so obvious is that there is a cross diagonal in the checkerboard, and if you reflect about that, they're actually the same representations. So you've got to make its reflection symmetric. And once you do that, everything drops out absolutely perfectly. And you get the gauge and gravitational interactions of the component fields. They just drop out. The main point that I want to stress is that the analog of the covariant derivative is this. It's the combination of the space-time part and the property part. That's what it is. This is how it arises in this scheme. This is a version of covariant differentiation. Now, when you do all this, you've got to be a little bit careful. You've got to choose the adjoint correctly with the right signs. I mean, these are just technical things, actually. And in the expansion of the super Fermi field as powers of zeta and zeta bar, it turns out that you get two bits, a field and its complex conjugate, obviously. And it turns out that the complex conjugate term just doubles the eventual answers. So you can actually simplify the calculation by just halving the expansion to just these terms. It just saves you a lot of work, that's all. Another interesting point is that if you go back to this, there are super gamma matrices. These guys here that multiply the Vielbeins. And you've got to make sure that the square of these things reduced to the usual square p squared. So if you look at the space-time part, you get the usual, nothing special. That's the Clifford algebra, obviously. But if you look at the property space, you get some really odd stuff here. You have two fermionic objects whose commutator is this. It's queer. And I struggled to see how on earth do you solve those equations. And I found a way, but I'm not 100% happy with it, but it works. It turns out that if you write the property gamma matrix, and if you define a set of coordinates from 1 to n, just like you have the zetas, and if you define the gamma to be the a sigma, a 2 by 2 space, the theta of it, the first coordinate. And if you look at the adjoint and make it the derivative, and if you make the field to be a singlet of that group, you do in fact satisfy the super Dirac algebra, or whatever you want to call it. Now, I have a feeling there's a better way of doing this, but I haven't found it. And if anybody's got any suggestions, I'd be very happy to entertain them. So now let's apply it. I'm going to confine myself to coordinates zeta1 to zeta4, and I actually don't only need them. I only need color and electromagnetism. These are the only forces that, so far as we know, are parity invariant. And I'm going to have two separate property invariants, the color invariant and the electrical invariant, which can appear in the property curvature polynomial. Well, if you do that, and if you may assume that these property curvature polynomials are the same in the property space and the gravitational space, then this is the general form of them. You can have as much as all that stuff. It's on the fourth line up. Well, if you do that, then the gauge fields turn up through the frame vectors. And this is where the quantum numbers turn up. You have the coupling constant multiplying the coupling times the gluon field. And this is telling you that it's also got charge minus the third. And the electrical field is charged -1, okay? And this is how it comes in. So you can then, once you know that, you can work out the gravitational elements. You have to work out the superdeterminant. They're all technical things, okay? And then when you multiply everything together to get your final thing, I've just written out on the third line what it looks like. You get the usual electromagnetic term, fine, and you also get the gluon term. It just drops out. And if you do the integration, this is what you get. And now I'm going to make a really significant point here. You've got to make sure that the normalizations of the electrical field and of the gluon field are the same. If you don't do that, you will not get gravitational universality. They've got to be the same. So you have to set CEF squared to be 4CEF E squared. Well, you can do that. It's not a problem. You can do that until you have independent couplings for electromagnetism and the strong interactions. And I won't, it's a long story. The color and electromagnetic interactions of the matter fields do emerge as expected. Now I'm going to do the last part of my talk. I'm going to talk to you about electroweak relativity, which is something a bit more complicated because you have to distinguish between left and right fermion. There are distinct properties because they have different hypercharged quantum numbers. It's a pain, but that's true. This is what makes the standard model so ugly, but that's what it is. So, the hypercharge of the left and the right neutrinos and electrons is going to be this is the usual stuff. Now, I'm not going to use the full SU4 gauge field. All I'm interested here is to try to reproduce electroweak, the original honest-to-goodness model of leptons, see what I can get. So all I require is the SU2L cross U1 rotations, that's all. And if I do that, then the off-diagonal element in the property space-time sector has the usual weak interaction constant. Then there's the hypercharged one, which I call B. And finally, it's sufficiently general for the purposes of this talk to take the property curvature to be a product of property right and property left. That's enough. Then you have all the invariants put in. Well, then you have to crank the handle. And when you integrate over the property coordinates, what you get is, of course, the usual Yang-Mills, Lagrange of the weak bosons, and then in addition the hypercharged ones. It just drops out with various coefficients. Now, once again, I have to stress, you have to make sure that the normalizations of these two fields are identical, otherwise you do not get gravitational universality. So you've got to make sure the coefficient of the B squared term is the same as the coefficient of the W squared term. And if you do that, you get a relation between the hypercharged coupling, G prime, and the SU2 coupling. Okay, so you can find a relation like that. Now I'm going to make a big assumption here, and I think you'll all go along with it. I'm going to assume that gravity can't tell the difference between left and right. I don't think anybody's going to kind of dispute that. So I have to make sure, therefore, that the coefficients of the left and the right invariants are all the same, because that multiplies the G as well. And and here comes the punchline. If you do that, you find that the weak W coupling is related to the Y coupling. It's really interesting. In particular, you get a prediction that the weak mixing angle has got to be 30 degrees. This has come from a completely left field here. Well, maybe left-right field. It's come in because you're imposing gravitational universality. Well, once you've done that, then you have to look at the matter fields, and you can do the matter fields. There are actually 2 generations if you do that. It's not the same as the standard model. You get 2 generations, psi and psi prime. And if you look at the super Bose field, you get a quartet of fields in particular. This is the one that's interesting, this one here. Phi mu, the one that's on that line there. And there are various quantum numbers. And the question is, where's the Higgs if you do all this? And I'll show you that the Higgs field is associated with the diagonal element phi 0 plus phi 3. So anyway, when you do this, and you turn the handle and so on, and work out the field bands of this model, and you do your integration over property, you get precisely the standard model. It just drops out. It's really perfect, except you have 2 generations. And if you want, you can even put let's go back. You can even choose the angle to be 30 degrees if you want, which it very closely is, by the way. Now, the question is where the masses come in, and the masses come in through the interactions of the gauge fields with the matter fields. And if you sit down and work it out, it turns out that it comes in through the product of the square of the phi gauge field term. And if you sit down and work it out, this is what you get. I can't have time to go over this. I'll discuss it with you if you're interested later. What you find is that these are the contributions, and if you want to make sure you get the correct masses, you've got to make sure the expectation value of this one is 0, which means these 2 have to be the same. In fact, the phi plus is just the vacuum expectation value that everybody knows and loves. When you do that, lo and behold, you get the correct masses for the W and the Z. And if you want to take theta to be 30 degrees, then you find that actually Z couples axially to the 2 charged leptons. Well, I'm running out of time. Let me just tell you, you can obtain masses for the fermions as well through the Yukawa interaction. It works out. You find one massive set of fermions and one massless set of fermions. It's not the standard model. It's more than the standard model. And if you want to see all the details of all this stuff, just put a reference, and you can find all the previous references in that one if you're interested. So I think to conclude, I'll just say that to fully handle the complete standard model gauge group, rather than bits and pieces as I have done so far, it's going to require more calculational dexterity and future research. Enough to say that we've come across obstacles in our work, and who doesn't? It's good to have birth pangs, otherwise you haven't achieved anything. And so far, we have circumvented them all. Whether we'll be able to overcome looming problems is quite another matter. It may turn out that the predictions which emerge will not be able to withstand experimental scrutiny. So far, we've set our sights on reproducing the standard model with the particle generations automatically catered for. That's the point. And if this procedure succeeds, we can look farther afield, seeing as we've really barely scratched the surface, actually. A left-right symmetric model is beckoning to us. Sterile states that don't interact with the basic constituents do exist and may represent dark matter if you think fancifully. And actually, if you would think about the quantization, that seems very natural in this scheme because they're associated with ghost fields which have exactly these kind of properties, okay? Now, let's be very cautious here. If we just be a bit more restrained, it may turn out that the future will judge this whole crazy approach of Hobart to be totally misguided. It may happen. After all, just one ugly fact can slay a beautiful hypothesis. The history of physics is absolutely littered with these failures. If so, you can forget about the present scheme and it can be buried with lots of others. Valiant attempts in the graveyard of failed theories, but maybe its ghost will linger a while. Anyway, in conclusion, I'd like to thank the organizers for inviting me to talk here, and I would like to thank them also for their generous support. Thank you all. That's all, folks.
Bob, you mentioned there were some additional quarks you had that charge 4/3,
yes.
plus or minus 4/3.
Yes.
And on the other hand, you say you have only two families, two generations.
No, we have the two isodoublets, and then there's some more. This is the third generation.
There's a third. So you have
Yes,
three.
there are three.
So you have three full families of the usual standard model.
Yes.
SU3 cross SU2 cross U1.
Yes, yes.
With the additional fermions.
With an additional.
And they are still anomaly free. There are no gauge anomalies.
Well, because if you look at the charges, it's a third, a third, a third, and -1, so anomaly should cancel in principle.
Salam's supervisor at Cambridge was Nicholas Kemmer, as a matter of fact.
Really?
Yes.
But I knew he went to Hoyle first.
He got advice from Hoyle. It was Hoyle who told him to do physics
Oh, I see.
after he'd done his mathematics.
Okay.
You said gravity doesn't distinguish between left and right,
Yes.
but you wrote a paper with Salam on axial anomalies for gravity.
Yes. But gravity still, that's fine. It doesn't contradict that statement.
I'm sorry?
It doesn't contradict what I said.
So what did you mean when you say it doesn't tell the difference?
It couples equally to left and right fields.
Oh.
That's all I meant.
Well, I could couple it to a neutrino. Gravity to a neutrino.
Yes.
That's not...
Well, we'll discuss it later. Okay. I take your point.
Maybe I can ask a question. Do you have any sort of orthosymplectic symmetry?
I have a symplectic. So actually, SP10 is the overarching group here, actually.
Is it orthosymplectic that mixes your property anti-commuting coordinates
Yes,
with the
that's
axis?
right, yes.
So what is the group?
This is the biggest group you can think of, the SP.
Is it OSP?
Well, I don't know if it's SP. Then in the property space, it's SP. But if you include the space-time, it's OSP. Yes.
So you do have an OSP symmetry?
Yes, correct.
If there are no further questions, let's thank Bob again.